I welcome you all in this lecture on bond graph modeling, which is a sub module for modeling and simulation of dynamic system course, which you are going through. The bond graph modeling concept arises because of the need of two things, that is the need to model systems which are in the different energy domains, as well as because of the way to find out how we can generate the system equations for the system in an algorithmic manner. So, this was the principal driving force behind the invention of the bond graph modeling. So, as we are dealing with the diverse systems or diverse fields, the system any modeling system should be able to take care of that diverse field. Now, one way to deal with diverse field or diversity is to achieve the conceptual unification. So, if there is some conceptual unification, we can deal with the diversity. Now, the requirement for a unified approach for modeling, simulation, as well as synthesis of physical system which resides in multi energy domain could be summarized into these. Okay. So, these are the requirement of the tool, that is the language for modeling should have concise lexicon valid over a large variety of energy domains. So, whatever language we are going to use for modeling, it should be valid over large energy domains, and it should allow the modeler to portray the exchange within as well as across the domains. So, this is another requirement, and as I told you, the portrait whatever has been created this way should algorithmically lead to mathematical or logical models, and of course, these models can then be subjected to say predictive or deductive processes. So, these are the here the above three are the basic requirement for the modeling method. Now, in the physical system in which we are more interested in, because we are talking about discussing about a course on modeling and simulation of dynamic system. So, the physical system in which we are interested in, it is the energy which plays the role of common currency of exchange between various domains, and that sustains the business of the dynamics. The idea of bond graph was proposed by Professor H.M. Painter at MIT, okay, and he used the graphical language for representation of physical system in multi energy domain through creating the exchange of power portrait. Okay. So, he could create a portrait of exchange of power through systems which are lying in the multi energy domain. Now, these portraits were further augmented by imposition of reference direction of power flow and causal relation, or what we call it as the information exchange. There has been a lot of work in bond graph modeling as a tool, and across say Europe or US or Asia, there has been many researchers who have been working in this one. In India, Professor Amlendra Mukherjee of IIT Kharagpur, he worked extensively in bond graph modeling, and in fact his group developed a modeling software which is very popular with the name as Symbols. The significant values of the portraits that may arrive as the portraits is that here one may arrive at mathematical or logical models in an algorithmic manner. So, as I have been talking to you in our introductory classes that the ultimate aim of any modeling exercise is to get the system equations, and once we have the system equations we can use the simulation tools to simulate those equations. Okay. So, the bond graph helps us in developing these system equations in an algorithmic manner. So, here this modeling method brought both algorithmization and unification. Unification because we can model systems which are there in the multi-energy domain. So, it unifies the systems in the different domains, and algorithmization means that the system equations are generated using certain logic or certain algorithm. Okay. And thus we have both algorithmization and the unification, and this fulfills the very important need of any modeling exercise, okay, to be carried out. Now, for engineering analysis and synthesis, computers could be deployed as our deductive partners and also could be entrusted to do the simulation. So, in fact, the software which I am talking about, or I will be talking to you in my coming lecture, in fact this software can do both the things. They can model your physical system, okay, and of course whatever system equations are generated at the end of the modeling process, those system equations can be taken or for the numerical simulation. Now, before we proceed ahead, let us see the invariant nature of the power exchange, which is the very principle, or what I can call it as the backbone behind the bond graph modeling. Okay. So, here the invariant nature of power exchange says that the direction of power flow at any moment is a system invariant. Okay. So, for a system, given system which we are dealing with, the direction of power flow is system invariant. What does this means is basically this one. Let us take a simple example. Here say there is an observer A and there is another observer B, and say both are holding a rod, and A is trying to apply a force in this direction, and because of that it is moving in this direction. Okay. Similarly, B is say trying to apply a force in this direction, but the rod is moving in say opposite direction here. Now, here the perception of A and B will be different. The A perception will be that A is pushing the rod towards B. Similarly, the B perception will be that B is pushing the rod towards A, but the fact is that the rod is moving from direction A to direction B. So, whatever be the perception of A and B, the power flow is from say system A to system B. This is what I mean by that the power flow at any moment is system invariant. The force are what we call in bond graph term as the generalized effort, and the velocity, which is terms in the bond graph as the flow, are its factor. Okay. So, the power basically is product of the effort and flow. This I am talking in general term. Okay. So, the power variables could be identified as the effort variable and the flow variable. Now, let us take system across the different energy domains, okay. And if you look at here say the various models which I have shown, say the first one is a block which is subjected to a translatory motion. Here in this case say the power is going to be equal to the force which is applied on the block into the velocity by which the block is moving. Okay. So, in this case the effort is force and the flow is velocity. Okay. Suppose I consider a rotary system. Now, in this case rotary system, suppose there is a torque tau is applied and the shaft rotates with say angular velocity omega, then in this case the power is going to be equal to tau into omega. So, the effort variable is tau and the flow variable is omega. Likewise, if I take the hydraulic system, here say say tank out of which the liquid is flowing out. So, the pressure here say is the P and the discharge is Q, then I can identify the power as product of the pressure and discharge, and here basically pressure is the effort variable and the discharge is the flow variable. So, likewise I can take an example of an electrical system. Now, in this electrical system you can say that there is a voltage source and of course there is a resistor which dissipates power. Now, here so you can see that in this case power is going to be equal to the voltage into current. So, voltage is your effort variable and the current is flow variable. So, here I have just shown only the 4 system. We can take examples from systems which are there which are from many more energy domains. So, this table basically summarizes the power variable for different energy domains. Now, here you can see that I have taken examples from the various systems, say mechanical, electrical, hydraulic, thermal and magnetic, and here the effort variables have been illustrated and in this column the flow variables have been illustrated. So, for a mechanical system, say mechanical translatory system, force is the effort variable and velocity is the flow variable. Like for mechanical rotary system, torque is the effort variable and angular velocity is the flow variable. Now, if I talk about electrical system, in this case voltage is the effort variable and current is the flow variable. For hydraulic system, pressure is the effort variable and volume flow rate dq by dt is the flow variable. Likewise, for thermal system I can define the temperature as the effort variable and entropy change rate as the flow variable, like pressure as the effort variable and volume change rate as the flow variable. I can also define the effort and flow variables for the magnetic system. So, the magnetomotive force Em is the effort variable and the magnetic flux rate is the flow variable. So, this way we can identify the effort and flow variable for any system which are lying in different energy domains, and once we have identified the effort and flow variables, then our bond graph modeling becomes easier. Let us take a very introductory example, what actually the bond graph is or how the bond graph looks like. All of you must be aware of the simple RLC circuit which is taught in say first year or second year of your undergraduate classes. Okay. So, here this figure shows you a simple RLC circuit which consists of a voltage source, say E, resistor, inductor and capacitor. Now, if I have to draw a bond graph model for this. The question is how to proceed, how to draw the bond graph model for this system. Okay. Now, let us assume that as I have been telling you that the power is system invariant here in this case in bond graph. So, here say there is a virtual power pipeline through which power comes to this circuit. Okay. So, a virtual power pipeline is drawn here, alright, and I am writing here SE because voltage is a source of effort as we have just seen in the previous slide in electrical systems. Okay. Now, then we have a resistor here, and as all of us know that resistors dissipate power. So, again assume that there is a virtual power pipeline through which the power is dissipated by the resistor. Then we have the inductor. So, for inductor here again inductor stores power. So, let us assume that there is a virtual power pipeline through which power goes to inductor, and here say there is a capacitor, capacitor again stores power. So, let us assume that there is a virtual power pipeline through which power goes to the capacitor. Okay. So, here basically at the first stage what we have done is that we have represented how the power flows across all the 4 elements in this physical model. Okay. Now, if I remove the physical circuit from the background of say this figure, then this is what we get. We have a source of effort, we have a resistor, we have an inductor, and we have a capacitor. Fine. So, here what we have done is basically we have replaced the physical circuits by its component, okay, and through these bonds we have just indicated that how that there is a flow of power to these elements, all right. Okay. Now, after this, so this is basically what constitute is that we have so many elements in the system and we have represented those elements by certain components. Okay. Now, the next thing is that how these elements are constrained here. Okay. So, if we look at the constraint, this is a simple RLC circuit, and in this RLC circuit it is a series RLC circuit. As we can see here, the current is going to be the same. Okay. Our current in case of electrical systems, it is a flow variable. Okay. So, the flow is going to be same across all these 4 elements. So, that thing we put here, or that identification that flow is same across all the element is done by putting here the number 1. Okay. So, this way it completes the bond graph. What we have done, we have represented the elements voltage source by source of effort, resistor by R, inductor by I, capacitor by C, and we have put the constraint here, that is the constant current constant, by putting the number 1 here. Now, for bookkeeping purpose, we can number these virtual power pipeline, or what we call it in bond graph modeling as the bonds, by different numbers, say 1, 2, 3, 4. Okay. And here just for our understanding I have written the different power variables in different bonds. Say for bond 1 it is E1 is the effort variable, F1 is the flow variable. Here one subscript basically means that it is related to bond number 1. Okay. Likewise, I define the power variables for the other bonds. Okay. So, this slide must have given you an idea of the bond graph modeling. Next, let us take another example. Now, suppose we have a resistor, inductor and capacitor, they are in parallel, okay, and they are connected with a current source. Now, here again if you go by the same concept which I discussed with you in the previous slide, this circuit is made up of a capacitor, an inductor, a resistor and a current source. Okay. So, here what I just do is, and all these elements are in parallel. So, basically this is how I can represent them here. Okay. And then I identify a current is a flow variable. Okay. So, here what we call it as the source of current is a source of flow. Okay. So, here there is a source of flow. So, I represent a SF, there is a resistor. So, I represent R. There is an inductor, so I represent it by I, and there is a capacitor, so I represent it by C. Okay. So, again we have a virtual power pipeline, and from through these virtual power pipeline or through bonds, the power goes to all these elements. Okay. So, this was the distribution of power across the elements. Okay. Next, what we put is that how these elements are constrained. Okay. So, in this case you can see that the voltages are same across all the elements, and that representation voltage is actually in general term we call it as an effort. Okay. So, the effort is same across all these 4 elements, and that is represented by putting a 0 element here. Okay. So, this is how we draw the bond graph for this physical circuit. Okay. Now, in these models, whatever you are seeing here, these models are further augmented by incorporating the power direction, which is nothing but as we put a coordinate system in the classical mechanics, and also we put a power direction by representing the half arrow. Okay. So, that is how it is done. Why to put half arrow? Because the full arrow is used as a signals bonds in the classical control system problems. So, to avoid the confusion with signal bond, here we are putting only half arrow, and just to indicate that these are the power bonds. So, the basic elements of bond graph. Now, let us come back to the theory of bond graph modeling. What are the basic elements of the bond graph? So, basically there are 9 elements through which we can draw any dynamic system, in fact. Okay. So, with the help of these 9 elements we can draw the bond graph model of any dynamic system. Now, these 9 elements could be classified as, say, sources, source of input. So, there are 2 sources, the source of effort which is represented by SE, and the source of flow which is represented by SF. So, these are 2 sources. There are 2 constraint also, as I talked to you in my previous slides about the 2 types of constraint, the constant effort and the constant flow. Okay. So, these constraints are the constant effort junction rather we use, because they indicate the junction of the different bonds. So, the constant effort junction is represented by 0, and the constant flow junction is represented by 1. Okay. And there are say 5 other main 5 other elements apart from these 2, and these out of 5 we have the inertia element I, capacitive element C. Okay. These 2 are actually the energy storing elements. Then we have a resistive element R, okay, which of course which dissipates power, and then we have the 2 energy 2 other elements, what we call it as the transformer element and gyrator element. Okay. And these transformer and gyrator, they in the bond graph modeling we call them as the 2 port element, because they interact with rest of the system through 2 bonds. So, the power and energy variables, the power variables as I talked to you, they are effort and flow, and the energy variables could be defined likewise as the momentum and displacement. Okay. And this momentum is defined as integration of effort of course from minus infinity to t. Likewise, the displacement could be defined as integration of the flow, and this minus infinity we can replace with say T0 by of course putting an initial condition as well here also. Next is the basic elements SE and SF. So, let us see a little description of these basic elements. So, we have, as I said, the two basic elements are sources, what we call the source of effort and the source of flow. So, the source of effort maintains input effort. The examples are the voltage source, forces or pressures, and this is how a source of effort is represented, and this example a voltage source is actually the source of effort. Then we have the source of flow which maintains input flow. The example could be the velocity source, current and the flow sources, and this is how it is represented, okay, represented by half arrow. And the source of flow is basically a good example can be given by the ground excitation of say on a suspension system of the car. Then we have the energy storing element I, okay. Now, energy storing element, these element I are used to represent the inertia or inductance, okay, and these are the effort storage element. Why effort storage? Because we know from Newton's law that Ft we write as m dV by dt, and from here I can write V as 1 by m integral Ft dt. So, here in the general term if I write it, so I have the flow is equal to say some constant into integration of Et dt. So, here you see that the effort is being integrated, that is why we call it as the effort storage, okay, effort storage element. And the I element could be the idealization of devices like mass, inductance, inertia in mechanical, electrical and hydraulic system respectively, okay. So, this way this can be modeled, and here you can see the different examples. Here it is an inductor, here example of rotary system, here the translatory system and a hydraulic system. So, through bond graph an inductor can be modeled and inductor can be represented like this. So, I colon we write L, where L is the inductance of the inductor. Similarly, here for rotary system I write I is equal to J, where J is the polar moment of inertia of this rotary system. Likewise, I can define the I element or inertia for a hydraulic system, okay. Next is energy storing element C. These are the compliance or capacitors. Compliance and capacitor can be represented by energy storing element C, and these are also called as the flow storage elements, okay. So, these are idealization of devices as devices such as spring, capacitor or accumulators, and this is how because they take power. So, this is how they are represented in the bond graph, okay. And why we call it flow storage? Because you see the displacement could be written as integration of the flow, that is why we call it as the flow storage elements, okay. And here you see say for let us take example for a compliance element, I can write effort as say the stiffness of the spring into the displacement or K integration of Ft dt, and this K I can in general term I can represent it by some constant G. So, effort is G into integration of the flow, alright. We can take various example, as I said in an electrical system a capacitor could be modeled like this with C being represented by 1 by C1, a spring can be represented like this with C being stiffness of the spring, and like in a hydraulic system the C can be represented by A by rho g. Similarly, let us see a resistive element R, okay. These resistive elements are idealization of devices like dampers, resistors, fluid carrying pipes, okay, and this is how they are represented in the bond graph. These are the dissipative elements and these remove energy and relates efforts to flow. Okay. So, as we have seen in case of say dampers, the effort is or the force is damping constant into the velocity. Okay. So, here I can write E is equal to R F, or I can write it other way as F is equal to 1 by R into E. Okay. So, as I said here, these are the examples. This is how in a general term it is represented with effort and flow being written as E F, the two power variables, and here R semicolon R I. So, for electrical system this R I is R say resistance here R. For a mechanical system this is the damping constant here, and for a hydraulic system here this is written as the hydraulic resistance RH. Likewise, we can define the other two elements. Okay. So, I will stop here and we will continue in the next lecture. Thank you.